Quantum mechanics shows us that reality is merely an illusion. It has been more than 100 years since we started decoding the universe at the tiniest scale. Over the years, we have discovered several intriguing phenomena in quantum physics, but the most interesting is quantum entanglement. This is such a mind-boggling reality that even Albert Einstein doubted its existence. He called it spooky action at a distance. To get an idea of how quantum entanglement works, consider this simple example. Suppose you have a pair of gloves, and you place two of them in two different boxes. After that, you shuffle the boxes and ask your friend to open one of the boxes. If he opens the box and finds a right-handed glove, then without opening the second box, you know that it contains a left-handed glove. This will remain true even if you take the second box to the moon or anywhere in the universe. That's because the two gloves were entangled entities and had a connection between them. One was right-handed and the other was left-handed. But things become spooky when you try to apply this principle to particles in the quantum realm. Particles have an intrinsic property called spin. Before you measure it, it can be in any direction. To measure the spin, first you need to specify the direction in which you wish to measure it. If you want to measure it horizontally, then the two possible outcomes will be left-handed or right-handed. If you wish to measure it vertically, then the two outcomes would be either up or down. Consider the spin of two particles. As mentioned earlier, before measurement it can point in any direction. Let's now measure the spin of one particle along the horizontal direction. Then the measured spin will be either right or left, each having a 50% chance. Even if you select the second particle for measurement, you will get the same results, 50% right and 50% left. However, if the particles are entangled just like the gloves, see what happens. If you measured the spin of the first particle and found it right, then the outcome of the second particle will be 100% left. So, the information of measurement got to the second particle the moment the first measurement was made. And here's the spooky thing: this information is transmitted instantaneously. If you make the measurement in one part of the universe, the quantum information can be sent to the entangled particle instantaneously, even in the opposite part of the cosmos. Remember, traveling at 300,000 kilometers per second, light is the fastest thing in the universe. But quantum entanglement is independent of it. So far, it was believed that quantum entanglement is purely a quantum phenomenon. However, scientists have recently observed this spooky action on a macroscopic scale. Entanglement is actually a correlation between two things. In the experiment, two teams of scientists crafted two aluminum drums of a red blood cell size. Each of these drums has roughly 1 trillion atoms. They placed them on a crystal chip and supercooled the setup to near absolute zero. Finally, they hit both the drums with microwaves. Struck by the microwaves, each drum vibrated, rising up and down by about the width of a proton. This minuscule motion was detectable as a change in the voltage of a circuit connected to the drums. When the drums are entangled, their amplitudes will be correlated. If one drum is measured to have a high amplitude, the other must have a low amplitude. The experiment was set up so meticulously that there was no way the drums could communicate with each other mechanically. The microwaves served as the intermediary that lets them talk to each other. You might be wondering what the purpose of such experiments is. As things become large, they no longer exhibit exotic quantum behavior. The goal of such investigations is to bring something big into the quantum realm. The applications range from quantum computers to problems in physics that require subatomic precision, such as the detection of dark matter or gravitational waves. But perhaps the most compelling aspect of the work, beyond any applications, is that it simply brings us closer to the true quantum nature of the world.